Alright, now we're going to talk about the common ion effect and how that applies to solubility equilibrium. So if we try to dissolve a solid in a solution with either the cation or the anion already present, less will dissolve. It's basically going to shift that equilibrium back towards the other side. And you've already had some experience looking at which way an ion would make it shift. So this is just the math that follows that up. So we're trying to calculate the molar solubility of strontium sulfate with a KSP of 3.2 times 10 to the negative 7. And we're going to do this in a solution of 0.010 molar Na2SO4, so sodium sulfate. Now, this is not a slightly soluble salt. Anything bonded to something in group 1 is totally soluble. But this does have an ion that is common to the substance, or to our slightly soluble salt, and that is the sulfate. They both have the sulfate involved. So what we're going to do is we're going to look and see how much of that sulfate is actually going to be in solution. Now this one will not reach equilibrium. It's going to split into its ions, and I'll have 2 sodium ions for every sulfate ion that is also produced. And this is 0.01 molar. Well, we can use mole ratio to help us figure out how much sodium ions there are, but we're really not interested in that. We've already identified that sulfate is the one that is going to affect our solubility equilibrium. So if I have 0.10 molar of this, it's a 1-to-1 mole ratio. This is 0.01 molar as well. All right, now we're going to create our icebox. And we don't have to worry about the solid. I went ahead and wrote my equation earlier. At the beginning, I'm going to have no strontium ions. And here's where it's different. At the beginning, I am going to have some sulfate ions coming from the sodium sulfate, not from the strontium sulfate. So I'm going to go ahead and put that in here at my initial. Now, how many ions is this strontium sulfate going to produce? I don't know. Let's make it X. So plus X on this side. We're on the same side of the arrow, so this is also going to be plus X. So this is going to be 0.01 plus X. Now, we're going to write our equilibrium expression for this. So KSP is equal to, for this reaction, strontium ions times my sulfate ions. They're both 1-to-1 mole ratio, so I don't have to worry about any exponents here. And now I know my KSP is 3.2 times 10 to the negative 7 equals my strontium ion concentration, which is X, times my sulfate ion concentration, which is 0.01 plus X. Now, this can end up being one where you would need to use the quadratic. But remember that this is a slightly soluble salt. And from the KSP, we can tell we're not going to form very many ions. So whatever X is, it is really small, and it's really going to be small when you compare it with this 0.01. So we're going to make a little simplification here to avoid the quadratic, although we could do that just as easily, and simplify it so that it looks a little bit like this. Now it's very, very easy to solve for X, and so 3.2 to the negative 7 divided by 0.01 is going to give us what X is, and X ends up being 3.2 times 10 to the negative 5. That is how much of this strontium sulfate was produced, or the strontium was produced. And this again is in molarity. So that's how many moles of ions. And for every ion of this produced, there's one of these that's actually splitting up. So that means there are 3.2 times 10 to the negative 5 moles of strontium sulfate, that will dissolve in every liter. So that is its molar solubility right there. This is a very similar problem dealing with that common ion effect, except we're dealing with, it's the same sort of problem, dealing with that strontium sulfate. So I went ahead and wrote out my equilibrium expression here. This time we have a different solution here and a different common ion. In this case, this is written incorrectly. There should be a 2 there. In this case, the strontium ions are the ones that are going to be common to what I have here. So I'm going to take my soluble salt, because all nitrates are soluble, and I'm going to split this up, and it's not at equilibrium because this thing is just going to, it's a strong electrolyte. I'm going to form 2 nitrate ions. Alright, so I'm going to end up with 0.01 molar of this, and 1-to-1 mole ratio with strontium is going to be 0.01 as well. I could also figure out nitrate, but that's not of interest to me dealing with these slightly soluble salts. So now I'll do my ice box. Don't have to worry about my solid, and I know at the beginning I'm going to have no sulfate ions, but I am going to have some strontium ions there. This is going to produce some ions. How much? I don't know. Let's call it X. And then we're just going to move our change around, and this is going to be 0.01 plus X. Same sort of situation. I've got KSP is strontium ions times sulfate ions, and now I'm going to plug those in. 3.2 times 10 to the negative 7 is my KSP. Strontium ions are 0.01 plus X, and sulfate ions are X. Again, this X in comparison to 0.01 is going to be itty bitty, and so we can make some simplifications because again this is a slightly soluble salt. We can tell that we're not going to form a lot of ions by the size of this KSP. Now I can just solve for X, and again we get 3.2 times 10 to the negative 5. That's how much of that strontium sulfate, or that's how many sulfate ions were produced, or the molarity of the sulfate ions that were produced, and it's a 1-to-1 mole ratio with the amount of strontium sulfate. So my molar solubility of strontium sulfate is going to be 3.2 times 10 to the negative 5 molar.